Hi, so welcome back. We today want to focus on acids and bases. Of course, chemistry is everything bubbling and fizzing, some burner lamp or test tubes, and there is flame. Everything in chemistry we have have to run these experiments in the library in the laboratory, and we always need like some tools for the chemistry. You are dealing with the spatula as a spoon, or you need a glass, clock glass, or clippers. You have to wear safety glasses, gloves, and apron. It's very important to take care before you start any experiment. Okay. So now we are talking about the acids and bases. If we come to the definitions, Arrhenius, acids and bases, Arrhenius said acid is a substance that when dissolved in water increases the concentration of hydrogen or hydronium ions, which is sometimes we say proton, sometimes we say H plus, or even H3O plus. And H3O plus is the hydronium. So this is the acid. So the acid dissolved in water increase concentration of the hydrogen. Okay, so we come here to see the HCl, aqueous, it means in the water, can dissociate, give you H plus, chlorine minus, and all in aqueous solution. Aqueous means in water, and this, as you see, increases the concentration of hydroxide ions. So water is being used here with HCl. So the water is amphoteric. It means can behave either an acid or a base. Once you use HCl, HCl is an acid. So when you dissolve it in water, the water will behave as a base. So it means the base will be increased. If we come here to the lower NaOH, sodium hydroxide aqueous, so we have protons of sodiums and ions of hydroxide, all of them in water solution. So you can see here, Brinsted-Lowrey said, or both of them, they said have both. An acid is a proton donor and the base is a proton acceptor. So proton here is not that proton inside the nucleus. We are talking about a proton related to acid base. So the proton here is H plus. And as you see here, we have the equation HCl aqueous plus water will give you hydronium H3O plus and chlorine ions. So Brinsted-Lowrey acids and bases are always paired, always paired. The Brinsted-Lowrey acid donates proton, while the Brinsted-Lowrey base accepts proton. Okay, so we have to and see what's the Brinsted-Lowrey acid says. The Brinsted-Lowrey acid is the proton donor, whereas the base is the proton acceptor. So which is the acid and which is the base in each of these reactions? Now you look at here in blue, HCl plus water. So that will give you a transition state, which is Cl minus, H plus, H2O. And now this will end up for the complete reaction will be hydronium, H3O plus, and chlorine minus. Okay, so we started with HCl. So what is HCl? HCl already has a H, so it's a hydrochloric acid. It means hydrochloric acid is an acid and the water here is a base. Okay, we come to the urea, to the ammonia, NH3. NH3 with water will give you NH3H plus or H minus, and then you have ammonium NH4 plus and hydroxide ion minus. So now, what's the behavior here of the H2O? It will be acid because NH3 is a base. So now what happens when an acid dissolves in water? You see here the acid HCl at the top left, and you have the water. So now the H will immigrate to the H2O to become H3O plus, and then the Cl minus. So it means look like the hydrogen lost its electron for the chlorine. Chlorine increased by 1 electron, and the hydrogen lost 1 electron, so it will become like hydrogen plus. As we said in chemistry, hydrogen plus means lost electron. So water acts as a Brinsted-Lowrey base. Why? Because of HCl. So, and abstracts a proton from the acid. Whereas hydronium is formed, H3O, and now ionization of HCl and formation of hydronium, H3O plus. So if you see here, H2O plus HCl, so here HCl is a proton donor because it will give its hydrogen to other molecule, which is the water here. And then we end up with H3O and OH. So now Brinsted-Lowrey acids must have a removable acidic proton. Like example, HCl, H2O, H2SO4. So these Brinsted-Lowrey acids, they must have a proton donor. So HCl has 1 proton. H2O has 1 proton inside it and hydroxide. H2SO4 has 1 proton and HSO4. So be careful. Brinsted-Lowrey base, what is it? Must have a pair of non-bonding electrons, as we mentioned in previous. So must have a pair of non-bonding. In this case, we have NH3. We have H2O. You remember NH3? There is only 1 lone pair has for the nitrogen, and H2O has 2 lone pairs, which related to the oxygen, non-used, non-bonding. 2 lone pairs means 4 electrons. So salts, if we come to the salts, compounds that dissociate releasing neither proton nor hydroxide ions. Example, HCl, KCl, we have K and Cl. So what is it? There is nothing, no protons, no hydroxide ions. So I just want to correct this to be nor. So neither nor. So we come here, we see the KCl is a salt. Why? It has plus K minus Cl. So compound dissociate, releasing nothing, only ions. Property of acids. Acids taste sour. Indicates a blue litmus paper turns red, and methyl orange turns red. So that's because of the acid. A pH, acids have a pH lower than 7 on the scale of pH, and acids are proton, hydrogen, ion donors. Acids react with active metals, produce hydrogen gas, and acids are electrolytes. Acids neutralize bases to produce a salt and water. So that's the property of acids. Acids change indicators. The litmus paper blue one will change to red. You see this red spot? So that's in the presence of acid. So a blue litmus paper turns red in contact with an acid. Acids react with active metals. So acids react with active metals to form salts and hydrogen gas. And you can see here magnesium with HCl, 2 mole, it will give you magnesium chloride and hydrogen gas. Acids neutralize bases. Why? HCl with NaH, NaOH will give you the salt and water. So neutralization reacts always produce a salt and water. Now acids are proton donors like monoprotic acids, diprotic, triprotic. So if you know there is one hydrogen here, so it's a mono. So it means one hydrogen donor, like HCl, HC2H3O2, and nitric acid, HNO3. Whereas the diprotic acids are 2 hydrogen there, H2SO4, H2CO3. A triprotic acid is phosphoric acid. So the uses, if we see the uses of these acids, you can see here in Pepsi cans, in vinegar, and as you see the H3PO4 in soft drinks, fertilizer, and detergents. H2SO4 as a fertilizer or in car batteries. We can see uses of hydrochloric acid in gastric juice for the drink. And you have the vinegar of this one being used in making vinegars. So everything here is the fizzy drinks or any pre-prep food or drinks contains acids. Acids, you must know, strong acids like sulfuric acid, hydrochloric acid, nitric acid. And like hydrobromic acid, HBr, hydroiodic acid, HI, and perchloric acid, HClO4. Okay? Whereas the weak acids, you have phosphoric acids and acetic acid. Okay, CH3, COO, CCOO. So properties of the bases. Bases taste bitter. Effect indicator. The red litmus turns blue. Phenolphthalein turns purple. Bases are greater than 7 on the scale. Proton acceptors, and they are slippery if you touch. They neutralize acids to produce salt and water. Example of bases: sodium hydroxide in lye, NaOH, potassium hydroxide for making shampoo, and here making soap. Magnesium hydroxide is this, and calcium hydroxide in the lime. So we can see some kind of uses. So NaOH is a soap or saponification or kitchen cleaner. You can use this salt or hydroxide base anti-acid. NH3 will agriculture fertilizer. So naming acids, bases, salts, we name them as ionic compounds. So acids, binary, 2 elements. There is first hydrogen. So we call hydrogen peroxide or hydrochloride, or so you see hydrochloric acid. It's always H hydro at the beginning. Ternary, there is 3 elements. So acetate, acetic is acid, or like you change the IT to O's as well. So strong acids, this weak acids, assumed to be strong acids, 100% ionized in solution, and they are good proton donors, like this we said before. But weak acids, usually less than 5% ionized in solution. It means they dissociate weakly. They can dissociate in water. Weakly is not complete. So the strong acid will dissociate, will completely in water and fully completed to the right side to do the products, whereas the weak acids, they are dissociate slightly, and you can always find the acid in the solution with the dissociated acids, like H3PO4. So if you see here, strong acids, they completely form H3O plus and the base. So the strong acid is the HA aqueous with water, liquid, will give you the hydronium and the base. Weak acid, you can always find, you see, this is, okay, let's go back. Sorry. So you have, look, this is one direction of the arrow. It means the strong acid. Whereas the weak acid, you have 2 arrows here. One to the formation of the products, and we have some of the reactants still in the solution. So it's not complete dissociate. Always you find reactants and products. And you see here, if you dissolve weak acid in water, you can find the same weak acid and a little of hydronium and a base. So it's like 100% of the weak acid will dissociate, as 90% still and 10% is being dissociated. So concept test, which of the following molecular pictures best represents concentrated solution of the weak acid HA? Concentrated solution. So if you see here HA minus, HA minus, and there is a HA Okay. Whereas here, you have always the acid itself, lots of it. Here we have very little. It's like all of them being formed by proton and hydroxide. Only little bit left here. Whereas here you have still the acid is there and a little bit of them being dissociated. So which one is the strong acid? I can say this was strong and this is the weak because they didn't form products. They still always, they are there in the solution. pH. pH is very important concept. It's a measure of concentration of hydronium ions in solution. So that's the definition of the pH. It's a measure of H3O plus, or we call it hydrogen plus, or proton, or hydronium concentration in solution. And there is a meter for the pH as indicator with a wide range of color. And you can see here the range between 0 to 14, the scale. You can find an increase in the middle is 7, which is neutral. Okay, and to the left, you go down 6, 5, 4, 3, 2, 1, 0. These are an increasing acidity. If you go above 7 up to 14, you can find the increasing in the basicity. And now let's see what's famous products we have. Neutral in the middle, 7 pH, and you have acidic less than 7 from 0 to 7, and we have basics more than 7 up to 14. So you can see here the lemon juice pH is 2, lemon juice. Wine pH is 4. The rain, if you have a crowded city of cars, it will dissolve the gas, the hydrogen gases into the rainwater, and the pH, you can find it 5.5. So you come to human blood is 7.5. And baking soda, now we are increasing. It's a base. It's a basic. 8.5 is a base, but it's not that strong base. We have a soda, we call it, or a detergent. pH is 10. And then the bleach is very high in hydroxide, which is 12.5. And what else you have? Greater than 7. We talk about it. So common substances, we can see battery as the battery of the car, which has up to almost 0, is very high. So once you go down the 7, it means you are increasing the acidity. So now which one is more acids, tomato or stomach, gastric juice? Which one? Is it number 4 or 1? You can say number 1 is more stronger than 4. So which one is more acidity, vinegar or lemon juice? You can say lemon juice more or stronger than vinegar in the acidity. If you come to the milk, milk is almost like in between 6 and 7. So it's not that acidic. So we have here a pure water at 25 degree room temperature it will be 7. Number 7, neutral, is the water. And as we said, the water is amphoteric, can behave as an acid or base. It depends. And which will react. So we increase the basicity. Which one is more basic? Is it sodium bicarbonate or NaOH? So NaOH is more, the strongest like liquid is the sodium hydroxide. It's very ionic. It's almost like 12.5 or 13 on the scale, so it's the highest. So now from above 7, you go increasing basicity. So 8, smaller than 9. 9 is smaller than 14. 14 is the highest. But here, 0 is the highest in acidity. If we see here the, oh my God, so I need to change the color here. So now you have neutralization reaction. If you come to the acid and base, will give you always salt and water. HCl with NaOH will give you NaCl, table salts, and water. You can see here ionic in solution with solution. If you mix like NaOH as a solid with HCl as a liquid, you cannot like get a complete reaction unless you just mix and increase the temperature. But you have to use like some solution. This dissolve it in a water and this one in water, so you can have ions. These ions will react quickly and to give you complete salt and water. Okay, so KOH with nitric acid will give you water and potassium nitrate. And this is the acid, HNO3. And this is the acid, and the base is KOH. Salt is what? KNO3. HCl with an AOH will give you this, as we talked about. Sulfuric acid with calcium hydroxide will give you calcium sulfate and water. And here, potassium with nitrate, potassium nitrate, and there is a water. So now the products of neutralization are always salt and water. If you want to neutralize acid base, so you end up with salt and water, salt, water, salt, water. We come to the buffer. The buffer solution resists changes in pH. So that's buffer solution. Resist change in the pH when a small amount of acid or base is added. So small amounts of acid or base, if you add it, it will resist. So no change in the pH. Or when the solution is diluted. So if you dilute the solution, so the buffer will maintain the pH. So this is very useful for the maintaining pH for the reaction at an optimum value. Buffers consist of mixture of weak acid and its conjugate base. Weak acid and its conjugate base. Or a weak base and its conjugate acid. So that is, we have a weak acid and its salt, weak acid and its salt, or weak base and its salt. Okay. Now, it's like we have the weak acid with its salt or weak base with its salt. Buffers helps organism maintain the pH of body fluids within the narrow range necessary for life. So even buffers helps organism maintain the pH of the body fluid. So a combination of proton acceptors and donors forms in solution of weak acids or bases. It's so every time if you add proton, so you can for the weak acids and bases. So accepting proton from solutions when they are in excess, and by donating proton when they are depleted. Okay, so the buffer solution always have to maintain the pH. Capacity of the buffer, amount of acid or base that can be added without causing large change in pH. So it's like you have, that's the amount of acid or base can be added. We said a trace of it. Trace of acid or base can be added so it won't change much in the pH. Physiological buffers, normal blood is between 7.3 to 7.45 on the scale of, and you see here is what is it? pH of the blood is a little bit higher than the neutral. It's like bases. There is a base because more than 7, it's basicity. So blood maintained to pH due to presence of buffers in it. Okay, so yours buffer system in blood, hemoglobin, oxyhemoglobin, 62%. So these are the buffers in the blood. What is it? Hemoglobin and oxyhemoglobin, which they contain or they value 62%. If you have H2PO4 minus, HPO4 minus 2 is 22%. Plasma protein is 11%. And all of these are buffers. And bicarbonate 5%. So as you see here, there is some acids, there is some base, there is some. So these all buffers and can maintain the pH of the blood. Oh my God, here there is a. Okay, let me check if there is any. So review, name the acid, base, conjugate, acid, and base. Oh my God, so there is something. I have to move it. So if you see here, this is the double arrow here. If you see double arrow, it means what? Now, if we see here, let's check now. So if you have CH3NH2, methylamine with water, you can find methylamine plus and hydroxide. So where is the, so methylamine NH2 is what? Is a base, and the water will behave as an acid. So the conjugate acid will be the CH3NH3 plus. So if you have a base, so you need to have OH outside. There is an acid, so the next, which one the accepted the proton will be the conjugate acid. Conjugate is it's like it's the acid itself, but after accepting the proton. So base, conjugate base. Always, if you have a base, you end up with hydroxide. So that will be conjugate base. But the acid is acting as an acid. Which one is accepted the proton will be the conjugate. acid. H3PO4. Now, H3PO4, you know it. What is it? It's an acid. So the water will behave as an base. Now, if you have this acid, we need the conjugate acid, which H3O. You see the conjugate acid? And then if you have a base H2O, you have H2PO4 minus is a conjugate base. Now we come to CH3COOH. So acetic acid with water. What will give you? Will give you, so the acetic acid and water. The water will be base and the acetic acid will be acid. So acid and conjugate acid will be H3O. This is the H3O plus. Conjugate acid, then whatever is base, you end up with another base, conjugate base. Now we have NH3 already. Okay. Now you have here as H2PO4 minus. H2PO4 minus. What's that? That has already lost proton. It was H3PO4. When lost one proton, so it's took its electron. So the electron will be at the minus above. So okay, an acid lost its proton. What does it make? So now you have the acid is CH3 and NH3 plus 1. Why? Because this already took extra proton. It has extra proton, so it's an acid, where this is a base, H2PO4 minus is a base. And then you end up with H3PO4 as an acid, is what? Conjugate acid. And then that one, it will be the conjugate base. So you see, whichever is behaving like an acid, it's in plus. Either you know the acid itself before protonation, deprotonation. Before deprotonation, you know the acid. It was CH3 and H2. See the first equation. CH3 and H2 was a base. But when accepted one proton, it became an acid. An acid. So in this case, the acid formed conjugate acid, which is H3PO4. You can opposite, reverse it, and you will find H3PO4 is an acid, sulfuric acid. So we name the acid base, as we said before. Again, there is a disaster here. We have to move these arrows. Okay, now we come here and see which one is the acid and the conjugate. So H2PO4 minus and OH minus. What is happening here? If I come to what's forming, so there is this OH, it's a hydroxide. Hydroxide is a base. So H2PO4 will behave as an acid. So what is the conjugate acid? It would be HPO4 minus 2. This is the conjugate base, and the acid will be H2O, because you can see here the base is OH, and then the conjugate base will be HPO4 minus 2. So it's accepted more of the protons. I come to this one, HCN. What is it? Cyanide hydrogen. with H2O. So now there is a H here, HCN is an acid. So you have an acid, you end up with the water. The water will be base. And then you end up with the conjugate base CN minus. And H3O, this is hydronium. This is an conjugate acid. If you come to this one, NH3 is a base. Ammonia with H2O will give you ammonium and hydroxide. So this is base, acid, conjugate base, sorry, conjugate acid and a base. Conjugate base. You see, acid, NH4, ammonium plus will be conjugate acid, and that one base. NO2 with HCO3 minus. What we end it with, if you confuse with the left, you go to the right. HNO2 is what? Is NO2 minus, already accepted 1 electron, so it was a base. And HCO acid, so this will be the conjugate base, and that then acid, conjugate acid. Now problem and answers. Good. So find the pH of 0.7 molar HCl. Okay, so pH means HCl in a solution. Let me just do it like this. So if we want to see this, find the pH of 0.7 HCl molar. So pH means HCl in a solution of water. And because of 0.7 is what? 0.7 is molarity. Molarity, it means mole per a liter. So in strong concentration. Okay, so we have HCl. 0.7 is too much, is big concentration. So it means the concentration of proton is 0.7 belong to the concentration of proton, mole per liter. So HCl in water will give you proton, hydrogen, and Cl minus. So now the pH depends on this 0.7 molar belong to the proton concentration. So pH is minus logarithm concentration of the proton. We just replace the hydrogen concentration by 0.7, and this will give you 1.15. This is the pH of 0.7 molar HCl. So on the pH scale, if less than 7 means acidic. So example of strong acids, you have HCl, HBr, HI, HNO3, H2SO4, HCl, perchloric, and perchromic. You have HCrO4. These are all strong acids. Every time you find these famous acids, you give the molarity to the proton, to its proton. So the concentration molarity will go to the proton, and you can easily obtain the pH. Find the pH of 0.2 molar propionic acid when there is a Ka 10 to the minus 4.87. So if you use the calculator and you enter, check the value of equilibrium constant Ka, so you just in the calculator put 10 to the minus this, it will give you 1.35 times 10 to the power minus 5. Okay, so propionic acid in water, this is it. So we'll give you the hydronium and hydronium and this base CH3C H2COO minus. So now all these are aqueous, of course. Okay. Now these are aqueous, and we can say the ice, we can apply the ice, criteria, which is I is initial concentration, C is the change in concentration, and E in the equilibrium concentration. So we deal with the initial, which there was, it says pH of propionic acid. So it was originally for the before the initial concentration. So it was 0.2 molar. And I don't know what was the H, what was the OH or the base. It was 0,0 concentration. When it's changed, so this lost minus X, but forming H and OH, so they are both gained plus X. Okay, so initially, before we dissociate propionic acid in water, the only concentration we had is 0.2 for the propionic acid, but we don't know how much was the concentration of 0. So it wasn't dissociated yet. So after changing, this propionic acid has lost some of its concentration. We say minus X. But the hydrogen been formed and A, or the base, been formed. So they gained plus X. At the equilibrium, what happened? The initial minus the loss, and here we still have X and X. Okay, so the Ka been measured for the initial equilibrium reaction, so we can use minus X for later error in concentrations. Okay, Ka, what's Ka? This is the constant of the acid. Equilibrium constant for the acid A belong to the acid. So we multiply the concentration of the products divided by the concentration of this one, because water is liquid, so we don't consider it. Okay, so we know any constants, multiplication of the concentration of products divided by the initial reactant. So now, if in this case, always when there is a 1-to-1 ratio, but if there is here like 2 molar, we can put it at the top of the proton hydrogen. We can put here to the power of 2 if there is 2 mole here. But because there is 1 mole, it's a ratio 1-to-1. Okay, so most of the acids are in the ratio of 1-to-1, unless we balance the equation and see if there is any how many moles there. We can apply it to the top. So now we put this, and now we replace this concentration with what? With X, and this base with X, you see? And HA is this one. We replace it with 0.2 minus X. So we have the Ka value. This is the Ka value here. Replace this one. So what's missing? Let's see. So X here times X, and here is 0.2 minus X. Okay. Now, show you this what happened. You can see 0.2 minus X. Okay. So if you do the calculation here, it would be complicated. So this can be solved using the quadratic calculation, but there is another easy way called rule of 100 or 500, 1000, in which how much big or small value can be the concentration started with divided by Ka. So we are dealing with this value here, 0.2 minus x. Let's see what this is, the concentration of the what? Of the product itself. We said after the equilibrium. So we take the 0.2, the initial concentration, divided by the Ka. Divided by the Ka. Okay, so concentration divided by the Ka bigger than 100 or not? Let's see. So when we divide the concentration 0.2 divide by the Ka, we found it 14,814, which is high, bigger than 100. What we do? We ignore the minus x. So in this case, we ignore minus x, and only we deal with 0.2. Why? Because the value between the initial concentration divided by the Ka constant is much far from 100, 500 rule. So in this case, what we do, we can ignore minus x, and now only we end up with x squared. X squared divided by 0.2 equals to Ka. You see? So now x equals to this amount. So this is x is what? Is the concentration of the proton. Okay? So if I have a concentration, it's easy to find the pH. So the pH is minus logarithm H equals minus logarithm this amount, put it here, and the value become 2.78. Now this is less than 7, means acidic, but it's still a weak acid. Okay, so just we will take another example. I will change and see more of this. Find the pH of 0.4 molar of NCH3 by 3. When Kb, look, there is a Kb, but here finding the pH. How can I do the pH from the Kb? I should have POH first. Okay, just be careful. Now it wants from me pH, but here I have Kb. So all the calculation will be in the base, constant base. Once I finish and obtain the concentration, it will relate to the OH. And once we have the concentration of OH, we easy calculate the POH, which is equals to minus logarithm OH. You finish it, you put it in another equation, which is pH equals to 14 minus POH. And then you end up with a pH. So now use the calculator similar to that before. We have the Kb, so 6.3 times 10 to the minus 5. So what's here, the Kb represents when NCH3 by 3 is a base, then in water, you see, this is the base. In water will give me what? This is the base. This is the acid. So this is the conjugate acid, and there is a conjugate base. So now we apply the ice as initial concentration to the change concentration to the equilibrium. Similarly, the initial concentration was 0.4, but I didn't have any concentration before for this and this. It will be 0. Okay, now after changing, this has lost. So we say minus x, but now this is appeared as an x, and this is as an x. After equilibrium, this initial minus the loss of x, and this is the gain xx. So now Kb is what? The constant balance or basic constant, equilibrium constant comes from the multiplication of the products divided by concentration of the reactant. We ignore water because it's a liquid. And now I have here X and X divided by what? 0.4 minus X. And we have the KB here. This amount, you replace the KB. Okay, we will check. So now, similarly, we end up with 0.4 minus X. So now let's check the initial concentration divided by the Ka and see, is it bigger than 100? We put 0.4 divided by 6.3 times with 6,300, which is more bigger than 100. So we ignore minus X. Okay, we ignore minus X. So we end up with X squared divided by 0.4 equals to this. X value will be 5. What is it, X? X here is the OH concentration. So POH is minus logarithm OH. This is it, 2.3. This is not a pH. The pH is what? You remember, the 14 is the scale of 14. 14 means pH plus POH. Okay, 14. So if I come here and say that 14 equals to POH, sorry, I have to make it small letter, POH plus POH. You see, that's the scale of 14. It's all pH plus POH. Now, you take out the pH, it's missing. So 14 minus POH, which I found it here, 14 minus 2.3 is 11.7. Now, what's that? It's highly basic. So now we have a big base. And so this base is 11.7. So now you have the pH of this solution. Find the pH of 0.3 molar CH3COO plus when Ka equals, okay, now let's see what's this. This is already dissociated product. So now the sodium acetate salt came when you react ethanoic acid with sodium hydroxide. So why putting this salt in water? So the sodium from the alkaline metals has no effect on the pH. Okay, sodium here has no effect, can ignore sodium ion, but what attached to it is important. This one is important, CH3COO in minus. So CH3COO minus is a conjugate base of acetic acid. Conjugate base. Look, it's a minus, and this was plus. So this will become a minus. Why? Because it took one electron from the sodium. Okay, so this is important now. Conjugate base, acetic acid, can steal hydrogen back from water. So now I make the equation. So this is the main equation. I don't deal with Na. I only deal with CH3COO minus. In water will give me acetic acid and hydroxide. So here, what? This is a base. This is the conjugate base. This is acid. This is a conjugate acid. Conjugate base in water gives H plus, a basic solution, or not H. Now we come to the initial change equilibrium. Initially, this one was 0.3, and there wasn't anything for these two. Once changed, this lost minus x, but this being appeared as x and x. So after equilibrium, 0.3 initial minus the loss x, and the here being formed x and x. Now we need to find Kb from how the K of constant of the water is acid times K of the base. So the K of the water, constant of the water is what? 10 to the power 14. Okay, that's the concentration. Okay, let's say the constant. Now, the constant here being given is 10 to the power minus, you see here, Ka 10 to the power minus 4.76. So now, and this times the Kb. So Kb here, if you divide this on this, which will give you very small value, we are dividing. So the Kb is the multiplication of the concentration of these two divided by this one. And now Kb, we have it as a 5. This is the Kb, the new Kb, 5 times this to the power minus 10, which is very little, very little concentration, equals to xx 0.3 minus x. Again, similarly, if you do the initial concentration divided by the Ka, it will be more, so you can ignore the minus x. Ignore minus x, you go with the POH because we are dealing with Kb. So the POH is minus logarithm concentration of OH, which being found, this is it, is x 1.3 to the minus 3, which is 4.88. Okay, so the pH now 14 minus this will give you 9.12, which is basic. So from the first equation, there was a starter of conjugate base only. So no proton, no hydroxide to be considered. Okay, so find the pH of 0.7, NH4 and O3, and Kb of ammonia is this one. Okay, so now because being given NH4, this is NH4, it's a conjugate acid. You remember NH4? Ammonium. Ammonium came from ammonia plus proton. Together ammonium. So it's a conjugate acid. Conjugate acid. Which NH3 got a hydrogen from water. So NH4 and O3 plus water will give you ammonia and hydronium. Or you can say we don't deal with nitrate. We deal with NH4 plus. So it gives you NH3 and H plus. So now this is it's been given the Kb. Anyway, we go with the ice, initial concentration, change in the concentration and equilibrium. So 0.700. We lost in the change and this is being gained, XX. And after equilibrium, we have 0.7 minus x. So if you do the similar calculation of the 0.7 divided by the Kb, it will give you very far. So you ignore minus x. You end up with the, so here, starting with the NH4, a conjugate acid, so we need Kw. Kw equals to Ka times Kb. So what does it mean KB? KB is KW divided, yeah, KW divided by KA. KW divided by KA. And the KA here will give you this value. So now we put the Ka back. It's the concentration of ammonia times hydronium divided by the ammonia. Sorry, ammonium here. Oh God, so this should be NH4 plus. So there is a mistake here, NH4. Now you ignore the minus X, so 0.7X will give you what? The concentration of H. And now pH is minus logarithm H. You just put it down and you will end up with 4.7, which is acidic solution. And I think this is the relative, or yeah, we did this. Relative strength of acid and bases, which is the strongest acid here? Methanoic. This is the formula. Ethanoic, propionic, propanoic, 2,2-dimethyl propanoic acid. So you can see here is what we have. 3.7 pKa is 3.75, and this is 5. So which one is strongest? You remember from 7 down, whenever you decrease the number in the pKa, so you have strongest number. So the lowest number is the strongest acid. Here, the ammonia, you have methylamine, trimethylamine, phenylamine. Every one of them 4.7, 3.3, 4. So which one is the strongest? pKa. Okay. Sorry, pKb. This is the pKb, so it would be the strongest is this one, 3.3. So the higher Kb, is the lower pKb. Okay, so lower pKb, stronger base. Higher Ka, so you have to put it on the minus logarithm. So when you put it in the minus logarithm, it will give you a stronger acid. And now here, as we can practice conjugate acid of HSO4, conjugate acid. So this is a base. So the conjugate acid will be H2SO4. Conjugate base of this, the base. So you see here we increase the protons. So become an acid, conjugate acid. But the base, always you have sulfate. It's the conjugate base for this. Now, conjugate base of this one, COOH. So this is the acetates. You remember? Acetates, and so this is very high. So the conjugate base for it should be deprotonated of this one. So removing the hydrogen will give you minus. So this is the conjugate base. Conjugate acids of this. So I leave you with these, and you can see what does it mean, and you can follow that. And now we have here a practice of 1 mole of HCl mixed with 2 mole of NaOH. So which of these solutions make a buffer? You remember what does it mean, buffer? Buffer, you always maintain the pH of a solution when you add a little bit of weak acid or weak base. Weak acid. So 1 mole of HCl. What's HCl now here? Mixed with 2 mole of NaOH. This is strong. So are they making a buffer? No, because there is no weakness here. Everything's strong. Okay, HCl, strong acid, with half a mole of NaOH. Okay, half a mole. So half mole of NaOH will mix with half mole of HCl. What's remaining? Remaining half mole of HCl, half mole. Is it still strong? Same reason. It's still strong acid left over. There isn't anything means weak. We don't deal with weak. If 1 mole of HCl mixed with 2 mole of NH3, ammonia, strong. So you have, is a strong base, ammonia? Tell me, is a strong base? I guess so. So, HCl with NH3, leaving what will be NH4. So this took 1 proton from here and became a weak NH4. So there is a weakness here. So once there is a weak acids there, conjugate acids, so there is a buffer. Now, 1 mole of HCl mixed with 1 mole NH3. 1 mole, 1 mole. Okay, nothing left. So I don't think there is a buffer for number 4. No buffer. Number 5, 0.1 mole of NH3 mixed with 0.1 mole of NH4Cl. Okay, let's do the equation here. So you have NH3, NH4Cl. If you mix them, it will be NH2Cl and NH3. So adding weak base to its conjugate acid directly. That's number 5. So this is weak base, and this is the conjugate acid. So we have a weakness. And 0.1 ml of this acetic acid mixed with 0.1 mole of NaC2, sodium acetate. So do we have weakness here? Number 6. Acetic acid with conjugate base directly added. Yes. That's weakness, weak. 0.1 mole HNO3 with NaNO3. So now what we have, do we have any weakness here? Yes, number 7. So everything is strong. NH3 is strong, and this is the conjugate as the salt here is, you can see there is nothing weak. 10 ml of 0.1 molar H2SO4 mixed with 10 ml of 0.05 molar KOH. So what's KOH? Strong acid, number 8, strong acid with KOH. So weak acid with strong base. Okay, H2SO4, strong acid with a weak base, KOH will give you this. So left some of the weak in the solution, so yes. H2SO4. So 0.1 NaH2SO4 with 0.1 NaHSO4. So number 9, some weaknesses there. So strong, H2SO4 is strong. HSO4 is strong, so there is no weakness here. And number 10.1 molar of N, this is strong with Na2SO4. So yes, weak acid, HSO4, and sulfate. So that's the buffer. So we have a buffer solution here. Thank you.